All right, these are your lesson notes for section 1.5. We are getting into inverse functions. So consider these two functions right here. If f of x is equal to 2x plus 4 and g of x is half x minus 2. As far as inverses go, here's just a couple examples of what would happen if functions are inverses of each other. So if you look at what we have right here, if I were to use a domain of 8, so if I were to sub 8 into the f function for x, and then if I were to take that answer and plug that answer into the g of x function, what would happen? So here we are subbing 8 into the f function in for x, and you can see we come out with a range of 20. And if we take that range of 20 and make it the domain of the g function, so we sub that answer into the g function, you can see what happens. We get back what we started with. So what we started with, the domain of f of x, became the range of g of x. And so if you get back what you started with, that's how you know two functions are inverses of each other. So, and that's going to be the key later on as we get into this lesson. The domain of the original becomes the range of the outside function. Here's how that would look like with just letters instead of numbers. But for the same idea that whatever we started with here, we ended with, if they are inverses of each other, the same thing will happen on this one. So even with letters, if I took g of x, so x is our domain, and we take the g of x function and we plug it into the f of x function, we should get back what we started with if we do this correctly. So here we are taking g of x and plugging it into f of x, and if we clean all that up, you can see we get back what we started with. So again, the key on this is that the domain of the interior function became the range of the exterior function. And because we got back what we started with, that's how we know that these two functions are inverses of each other. And it wouldn't matter which direction you did this. We could also plug f of x into g of x, and notice again we're going to get back just x. And so that's how we know that these are inverses of each other. This is just kind of a side note for notation, but when we talk about inverses, they use the little exponent of -1 to represent an inverse function. And so here's just kind of the notation form of what we just did. But notice an inverse function of a function gives you a result of just x. Now this only works for one-to-one functions. You can't get an inverse function technically if it's not a one-to-one function. So a one-to-one function is simply this. If I have a graph of a function, it is one-to-one if I can draw a horizontal line through the function and only hit the graph once. So in other words, a function only has an inverse function if it passes the horizontal line test. So you guys remember the vertical line test from our past lesson. Well, this is the vertical line test, or sorry, the horizontal line test. The horizontal line test is used for testing to see if a function has an inverse. So this one does pass the horizontal line test, which means it is a one-to-one function. So this one does have an inverse, but if you compare that to this one here, he would fail the horizontal line test, which means it is not one-to-one, therefore does not have an inverse function. So here we're going to see inverses both graphically and algebraically. So this portion is basically the graphing explanation of inverse functions and how they work. The next part will be algebraically. I did include another video, a real short 2-minute video that also has a good explanation of domain and range for inverse functions when you're getting into the graphs, because these can be a little tough to wrap your head around. So I encourage you to take a look at that other little video that I have on the calendar right below this video. The guy had a pretty good explanation of domain and range. But simply put is this. If I have the function f that you see right here, so the original 2x plus 4 graph is right here for f. If I mirror that graph across the line y equals x, so this is my mirror right here, then I get the inverse function that you're seeing on the other side. So an inverse function is just a mirror image of the original function across the line y equals x. All that would happen is your x and y coordinates just trade places. So the point 0,4 would just become the point 4,0. And that's all you really have to do for an inverse function is just switch coordinates, and you create the inverse function. So here's something that might help on number 2, because number 2 is a little tougher to deal with. The key on this is, so you have to notice this was the original domain was 0, and this was the original range was 4. Well, look at what happened to those. They just traded places. So on the original function, you have domain and range. Those become the opposite domain and range for the inverse function. So in other words, the domain of the original becomes the range of the inverse. And the range of the original becomes the domain of the inverse. So that's key. So take a look at number 2 here. So we're starting out with the original function of x squared. And they're going to limit our domain, and I'll show you why here in just a minute. But they're asking for a sketch of the inverse function, and then they're asking for the range of the inverse. So I'm going to try to give you a little graphic explanation here of what's going on. But remember what we talked about. If I have y equals x squared, that would be a parabola, and that would fail the horizontal line test, which is why it technically doesn't have a proper inverse function unless you restrict the domain like this one does here. So let me give you a quick explanation of how that works. So if you see the red graph, we have the graph of y equals x squared, and here's the mirror of y equals x. And so if I were to reflect that across my mirror, and remember how we do that, if I have y equals x squared, to get the inverse, I'm just switching x and y and then solving for y. And I actually did that on the notes that you see right here. So if y equals x squared, if I switch x and y and then get y by itself, this is what we would get. But you guys know, just from basic algebra, anytime you take the square root of both sides of an equation, you're supposed to put a plus or minus right there. So if I did have the graph plus or minus square root of x, I can see the mirror reflection of x squared. So if I were to do the positive square root of x, I get that orange line right there. And if I were to do the negative square root of x, so negative square root of x, then I get the black graph that you see. And you can see this sideways parabola is my mirror image of the original x squared across the line y equals x. Well, why is this not a function? Remember what we learned in the last lesson. This inverse would fail the vertical line test, which means it's not a function, which is why when I look at the original graph and it fails the horizontal line test, that's the one that tells me that the inverse is not a function, because the inverse would fail the vertical line test. And that's why we can't do that. But if we restrict the domain, so the one that we're looking at says the domain is, I can only look at x's that are greater than or equal to 3. Well, if we ditch the negative portion of the graph, well, now what I have for the inverse does pass the vertical line test, so now I can work with it. And so that's why you're going to get a restricted domain on that, because now it's actually doable with an inverse. It's now a proper function. So going back to our notes, so we're only looking at x's that are greater than or equal to 3. That's our domain. So remember what I said earlier. The domain of the original function becomes the range of the inverse function. Then my range would be of the inverse function would become y values that are greater than or equal to 3. So right down here we're seeing the range of the inverse, and that should say y is greater than or equal to 3 for the range, simply because the domain of the original was this, so the domain of the original becomes the range of the inverse. So that should say y is greater than or equal to 3. So that's how we got the range. What about the domain of the inverse? So remember that the domain of the inverse would be the range of the original function. So what was the range of the original function? Well, if I could only look at x's greater than or equal to 3 for the domain, here's how we would see the range. So here was the original function. And if I go right here, so this is where x was 3. There we go, close enough. So for the original function, when x was 3, you can see the y value was 9. So if I can only use x's that are greater than or equal to 3, well, look at what happens to my y value if x becomes greater than 3. My y value goes up because I'm going to the right and I'm moving up the parabola. So for x is greater than 3, my y values become greater than 9. And so that's how we get the range of the original function. So if the range of the original function are y values that are greater than or equal to 3, well, the range of the original becomes the domain of the inverse. And so right here we have the domain of the inverse would then be x's greater than or equal to 3. So we always use x's for domain and y's for range. And like I said, I have another video attached to the screen on the calendar if you want to see kind of another explanation graphically for domain and range of inverses. And so right there at the top of your screen, number 3 is your basic explanation for domain and range of the original becomes the opposite for the inverse. So algebraically, how do you find an inverse? Pretty simple. You just switch x and y and then solve for y. So right here on part D, you can see the example. You basically have y equals 2x plus 4. So if I just switch x and y and then get y by itself, you got your inverse. So same thing on number 2. This was the original function. Notice they had to throw this statement in there because you can't have that 0 denominator. So that's just a proper way of stating what this function would have to represent. But if I, again, just take my original function and switch x and y, and then we just solve for y, get y by itself, that creates the inverse function. And then one more example down here for number 3. Again, we could do the same thing, and this is what we saw with the graph up above. This is the original function. If I switch x and y, and then get y by itself, and again, notice because you're taking the square root of both sides of the equation, you got to throw in the plus or minus statement. So here was the original y equals x squared. This is what the inverse would look like. Because you had to throw in the plus, so here's the plus side. So this is the positive square root of x. Down here you get the negative square root of x. So that's why we had to throw in the plus or minus. But by throwing in the plus and the minus, you get both sides of the parabola, which means it would fail the vertical line test. Therefore, this inverse does not really exist. The inverse is not a function.